morning, all of you. Good morning, all of you.
Good morning, sir.
Today your scheduled laboratory class is on the calibration of the three-phase watt-hour meter or energy meter. So I think all of you are familiar about the working principle of the induction Dix type energy meter or watt-hour meter. So the induction Dix type energy meter for polyphase systems or three-phase systems uses the two-element induction Dix type, and they have a common mechanical linkage. So with the help of the registering mechanisms, if we recall our basic knowledge or about the working principle of the induction Dix type energy meter, so according to the 2 watt-meter method, there is a two-element in construction. There is a two-element watt-hour meter for three-phase system, so that the torque, the driving torque, is proportional to the sum of the power consumed over a definite interval of the time, and that is called the three-phase energy consumed in a three-phase circuit or three-phase system. So this is a typical look of a commercial type three-phase energy meter, which has an Dix type, which consists of a Dix. The rotations of the Dix is an indication or is a measure of the energy is being consumed when the meter is input to the three-phase circuit. But how the energy will be, the amount of the energy consumed in a system will be displayed with the help of the mechanical counter with significant digits or in the form of the decade dial. So this is called the registering mechanism. That means when the Dix will rotate, due to the rotation of the Dix with the common shaft, there is a set of pinion or gear, the particular gear called the beaver gear. That means by which the rotation in one axis, horizontal axis or vertical axis, is transformed to the 90 degree, that is horizontal axis, and a set of decade dials are mounted, so that each decade dial consists of a pointer which can rotate in clockwise or anti-clockwise alternately, and at any the pointer will indicate the significant digit over the decade dial system, because each the dial has its 10 number of digits. These are marked with 0 to 9. So accordingly, when the indicator or the pointer passed away in a proper direction, forward direction to the particular digit by decimal system, that means with a multiplication. That means the number indicated by the significant digit multiplied by its position. For example, this is the least significant digit position over which the multiplying factor will be, after decimal point, it is 1/10 to the right side, and to the left side it is unit positions. It is 10 position, 100 position. So we can get, the user can get the amount of the kilowatt hour reading directly. That means kilowatt hour means the unit of the commercial electricity energy in the form of kilowatt. So that is the working principle, a brief working principle about the induction Dix type watt-hour meter. But what is more important is that according to the specifications of any energy meter is a meter constant. Meter constant is a least count, the unit of which is expressed in terms of the revolutions per consumptions of the 1 unit of the electricity energy or electrical energy, that is per consumptions of 1 kilowatt hour. So the number of Dix revolutions which will occur per unit consumptions of the kilowatt hour is called the meter constant or the least count of the energy meter. The significance of the meter constant is that means depending on the constant power flow, that is what, the speed of the Dix will depend on the value of the meter constant. For example, in our case, that means for this experiment, the test meter, that is the test whatever meter, as a meter constant as specified by the manufacturer is 2400 revolutions per kilowatt hour. That means when 1 kilowatt hour energy will be consumed, the Dix will rotate 2400. So the value of the meter constant may be high or may be low. What will happen? That means if the value of the meter constant is very high, that means the sensitivity of the energy meter will be definitely high, because the meter will be able to measure the smallest variations of the kilowatt hour. If the value of the meter constant is low, the sensitivity is low, which means that means the meter is not able to sense the small change in the help of by Dix rotation. So that's why the testing of the energy meter requires the calibrations of the meter constant with the help of the calibration experimental setup, proper experimental setup, whether the specified meter constant, how much is the specified meter constant to the value of the, with the value of the experimental value, and what is the percentage error of the meter constant. Anyway, according to the IEC rule, the testing of the energy meter is generally done to check the calibration and to registration mechanism, that means the dial rotation. So there are two types of the error that generally will occur in case of a watt hour meter. One is the error caused by the Dix rotation due to the mechanical problem, because the Dix will rotate according to the driving torque generated, and when the Dix will achieve the steady speed, because there is a brake magnet or the braking system, so with the help of the braking torque, the Dix will rotate with a constant or uniform speed depending on the energy consumption. So it is necessary to check the registering mechanism as well as the Dix rotation that may have the error. That means the Dix can rotate with a high speed or with a lower speed. So it needs that in the rotation of the Dix to be calibrated in terms of the meter constant or the error in meter constant, as well as the rotation of the Dix is mechanically connected or linked with the registration mechanism. So registration mechanism consists of a number of elements, that is a decade dial system. Each may cause its own error, that means error. So that's why there is another type of error which may cause by the maloperations of the registering mechanism. So in an effect, consequently, there is the two types of the error which will cumulatively occur. So the gross error will result in the error in the kilowatt hour measurements. So that's why there are definite. That's why there are definite. That means the testing of the energy meter is to check the calibration and the checking of the registering mechanism. So testing conditions are summarized as meter should be tested for the following electrical condition according to the IEC rule. At 100% or 125% of the rated current, because the voltage should be applied to the rated value and the current should be varied during the testing. So the test, the trial or the calibration should be followed according to these conditions, electrical condition, that is 125% or 100% at rated current with unity power factor. At 100 or 50% of the rated current, that means the load current, that means should be at a low value, 50% of the rated value with unity power factor. Again, the power factor should be varied with a 0.5 lagging power factor condition at the same loading condition, that is 100% or 125% of the rated load current, as well as 50% of the rated load current with 0.5 lagging power factor. So these are the testing conditions according to the IEC rule, electricity rule. What are the name of the testing? Short time test. Short time test means in which the meter error in the meter constant, percentage error in meter constant should be measured, or that is called the short time test. So what is the description of the short time test? That means a current coil of both standard and the and uses the substandard meter. In fact, the test meter is considered to be a erroneous meter. With the help of the reference of the substandard meter, what is the difference in value, that is the value in the meter constant as specified by the are computed by using the substandard meter, and with the value which is specified by the manufacturer, the difference is measured. So these are the description of how the short time test should be carried out. In short time test, the arrangement is made to record the number of disc revolution for both meters, that means using the substandard meters and the test meter or standard meter, over a short time interval of the order of seconds. In our laboratory case, experimental case, both we follow that means there are different types of the testing method. One is called the short time test using the substandard meter, following these conditions of the experiment, and the results are calculated according to this parameter. Let Kx is the number of revolutions per kilowatt hour for the meter under test. Ks is the number of revolutions per kilowatt hour of the substandard meter. Rs is the number of revolutions made by the substandard meter during the test interval. The interval may be like that. That means by using the stopwatch, how much amount of the definite revolutions the disc will complete, that should be fixed up. For example, 40 revolutions, 20 revolutions, or like that. Rs is the number of revolutions made by meter under test. Ns is the speed of the disc of the meter, test meter under test. Ns is the speed of the substandard meter under test. T is the time interval. Actually, by method, that means the method, T may be the time in seconds, that is what the fixed, say 60 seconds, 30 seconds. Truly speaking, the short time test follows this parameter, and using the formula, when the revolutions are compared, there are two computation rule. When the revolutions are compared, that means for a fixed amount of the revolution, like 40 seconds, which will be completed by the test meter, disc of the state meter, and the disc of the substandard meter, that should be followed. And these are the percentage error directly calculated using the formula. Now, when the speed, it is not followed generally. When the speed are compared, then the formula for the error computation is different according to this equation. Both the method can be, both the computation rule can be used here under short time test. So the short time test actually determine the error in the disc rotation. Then there is another testing method, what is called the long period or the dial test. In this test, the performance of the registering mechanism, that means in addition to the disc rotation, in addition to the error caused by the disc rotation, as the disc is mechanically connected to the common shaft to the registration mechanism, so definitely another error will be cumulatively will arise. So that error will be computed under the long period dial test. In this test, that means the long period means 30 over 30 minutes, or that means more than 30 minutes, that is 45 minutes, a fixed time should be used, over which the disc rotations, over which the readings of the meter, which are directly available from the decade dial system, should be noted. Without going through counting the disc rotation, the meter reading over the substandard meter and the test meters are noted down. And using the formula like this, the percentage error for the long duration test is calculated. So dx and dy are the meter reading over for the meter reading of test meter and as well as the substandard meter. But the time required for the long period of the dial test is much longer. So that is a disadvantage. The user has to wait at least 30 minutes according to the standard. Our laboratory method uses the third method, that is short period test using the standard wattmeter. That means whenever the calibration experiment is performed, so the test meter, the reading of obtained by the test meter should be compared with the standard meter. Here, instead of using the standard whatever meter, we use the standard wattmeter. Because we know electrodynamic type wattmeter are considered to be the standard meter in all types of the calibration experiment. That may be the calibrations of the wattmeter or calibrations of the energy meter. So short period test or the short time test using standard meter is our case. And the formula to find out the percentage error is given by this formula. It is easier to follow. The third test is called the test of the energy meter under no load condition. We know when the current coil of the induction disc type energy meter is switched off, that means no load current is flowing. So what will happen? No driving torque theoretically will develop. But it is due to the overcompensations, the different compensation method, that means lag adjustment and like that. So the shunt magnet is split into a shaded pole. So that's a name that there are two types of the construction. One is called the shaded pole and the Ferraris type. But generally the induction disc type is the shaded pole type. That means there is a shading band which will produce the additional flux which will help to lag the shunt flux perfectly more close to 90 degree. And we know when there is a phase shift between the shunt and the series flux, the series flux is produced by the flow of the AC load current. That's why the name implies that it is a series magnet. When the phase difference angle between the shunt flux and the series flux is more close to the 90 degree, the sensitivity of the energy meter, that means the sensitivity of the energy meter will be very, very high. So that is normally set by the lag adjustment method. But unfortunately, this also called this is also done with the help of the overcompensation or that is compensating using the compensation of the shunt flux. So what will happen? That means due to the splitting of the two fluxes, even though there is no series fluxes, a phase difference angle will result with a very small value, and that will cause a slow rotations of the disc type. Even the disc, induction disc, even the series magnet is not excited. So that means it will occur. That means the slow rotation is called the creep. The creep should be around as per limit should be half rotation per 24 hours or like that, very small. So that is allowed. But creep cannot be avoided. So there is a mechanical method by which the creep can be avoided. That means over the discs there is a need to drill a hole or drill a pair of hole on diametrically opposite direction, so the creep can be minimized. Now, what is the testing circuit? What is the experimental setup of the energy meter testing? The name is called the phantom loading circuit. That means two separate power supplies are used. One to excite the current coil of the energy meter, another to energize the potential coil or the shunt magnet. And there must be a phase shifting arrangement so that a different power factor can be made. So there must be a phase angle difference that should be produced by the phase shifting arrangement. So this is called the conditions of the phantom loading. Why phantom loading is required or necessary? For energy meter or the wattmeter testing, that means in case of a actual loading, the amount of the power loss that will occur over the meter as well as the load. But using the phantom loading or fictitious loading, so there is no physical loading to be connected to the meter. Rather, instead of which, the current coil is excited varying from 0% to the rated conditions, as well as the potential coil will be excited at a fixed rated voltage. This will occur the minimum amount of the power loss, and the power supply size of the power supplies or the capacity of the power supply will be minimum using the phantom loading circuit. Now, the phantom loading or fictitious loading arrangement can only be done in case of a wattmeter or the energy meter calibration. That will avoid the wastage of power. So with this arrangement, the phantom loading arrangement, the total power supplied for this test is that due to the small pressure coil current at normal voltage plus due to the flow of the rated current at the low voltage supply. Generally, in phantom loading method, the power supply for the current coil should have very, very small value. But the power supply, the rated voltage of the power supply required for to excite the potential coil is at the rated value, is a high value. So that is the condition. Now we come to the actual calibration experiment in our case, laboratory case. So this is the experimental circuit. You can view the experimental circuit, that means which consists of a three-phase step-down transformer, which has a low voltage secondary winding and the high voltage secondary winding, because the supply is 110 volt between 110 volt balanced three-phase supply, three-wire system. That means 110 volt with respect to the phase voltage or phase voltage. So line to line voltage will be 110 root 3. So that is applied to the three-phase transformer. And the secondary of the three-phase transformer, which are isolated, two of the phases are used using the 2 wattmeter method. So one phase will generate the 4 volt only AC volt. Another phase will produce the 4 AC volt, 4 volt AC RMS value. And this is the typical connection. That means via the rheostat, the current can be regulated to the current coil of the wattmeter as well as the current coil of the energy meter. So this is the test energy meter, potential coil, and this is the current coil of the test energy meter. And the current coil must be connected in series to the current coil of the standard wattmeter and the test meter. Similarly, for the other element, the same connections is followed up or used. And there is another phase which is required to excite the current coil. But the potential coil of both the standard wattmeter and the energy meter are connected in parallel to the another secondary of the another unit. This is called the three-phase phase shifter. The advantage is that means that primary of this three-phase phase shifter and the step-down three-phase transformer are drawn from the same side. It is a parallel connection. But the secondary of the step-down transformer as well as the three-phase phase shifters are different. What is the meaning? That means the secondary of this stator winding is phase shifted with respect to the primary voltage. In fact, there is a three-phase phase shifter, induction regulator type three-phase phase shifter. What is the induction disc type phase shifter? Now we can go or move to the this supplementary note, induction regulator. That means there are two types of the three-phase phase shifter or phase shifter, single phase and the three-phase. In three-phase phase shifter, what will happen? That means these are the connections of the three-phase phase shifter. There is a stator winding which is connected to a star, and there is a rotor winding which is three-phase, and the rotor can be rotated using the mechanical system, which is called the block rotor. That means so that no driving torque will be generated so that the rotor cannot move. Otherwise, what will happen? It will be an induction motor like that. So it is a block rotor condition, but the rotor can be moved, and especially with respect to the stator axis, especially it can be mounted to any angular position, so that what will happen? The final winding, which is a three-terminal or three-phase winding, this is consists of the two induced voltage. One is the primary winding, and another induced voltage is the phase shifted secondary winding. So this will be vectorially added, so that with respect to the common point, according to the phasor diagram, we get the resultant voltage V. V is the secondary voltage, which is called the phase shifted voltage with respect to the primary winding Vp. But this is the voltage which will be induced according to the spatial angular positions of the rotor. So the more will be the magnitude, RMS magnitude of this rotor VR, the more will be the phase shifting operation. And this is a balanced phase shifter, so the three-phase winding will provide the phase shifted voltage with respect to the primary input. So that is the working principle of the three-phase induction regulator type phase shifter. The same principle is utilized here. This is a three-phase phase shifter. This is a symbol of the induction regulator type phase shifting arrangement. So what will happen? Basically, according to the dial of the phase shifter, what is the amount of the phase difference angle between the rotor current, between the load current, that is according to the phantom loading circuits, and the voltage applied to the pressure coil of both the wattmeter and the standard energy meter, that can be varied. The test condition specify a test condition mentioned, that means in two power factor condition, that is unity power factor and the 0.5 lagging load power factor, that should be maintained. So that can be easily set with the help of the phase shifter. So this is a circuit diagram, and the rated load current can be varied by the two rheostat. One rheostat is used R1 in one phase, and another rheostat is used in another phase. So both the rheostats should be simultaneously adjusted in such a manner that means the amount of the current indicated by the two ammeter will be the same. So 100% here, the 100% rated current means the 5 ampere. According to the percentage loading, there are different percentage setting, so that according to the ammeter reading, we can adjust what will be the percentage rated percentage current loading to the current coil. So this is the Expenditure Circuit diagram, and these are the apparatus list which are generally required to carrying out the experiments. So 7 types of the items are used: polyphase watt-hour meter, that is the test watt meter, to rheostat, digital panel meter for voltage measurement, phase shifter, three-phase transformer, step down, delta star connection. The secondary is connecting star and the primary is connecting delta, because the supply system has a 3-wire system and the 3-phase variac. Where the variac is utilized, the variac is not shown here. In fact, here input to the 3-phase regulator, there is a 3-phase variac, so the voltage will be adjusted to a particular value. Additionally, so now follow the procedure, check connection according to Expenditure Circuit diagram, switch on the supply and adjust the voltage V to rated voltage, that is 110 voltage, and the current A to rated value, that is 5 amperes, 100% rated current is 5 amperes. Operate the phase shifter. Now we can use the knowledge of effect of the power factor on the 2-watt meter method. So what is that? Again, according to the supplementary note, we must follow this effect of the power factor on the 2-watt meter, this chart. When the power factor becomes unity in case of a 3-phase loading condition, both the wattmeter will indicate the equal value and the positive direction. So W1 will be W2. When the power factor lies between 0.5 and the unity power factor, that is the phase angle is between 0 degree to 60 degree, then the one wattmeter W1 will read positive and the another both the wattmeter will read this will be positive and positive, but the magnitude of the W1 will be greater than W2 when the power factor falls in this range. When the power factor is exactly 0.5, that is phase angle is 60 degrees, so one wattmeter reading will vanish. It will be 0, and the whole power will be measured by the another wattmeter, that is W1, and total power will be is equal to W1. We can use this condition, as well as we can use this condition from the 2-wattmeter method, that means using the 2-watt meter. Here the digital wattmeters are used, as well as 4 and the 5 condition are for different power factor conditions. When the power factor lies between 0 to 0.5, one wattmeter reading will be negative, back deflection, another wattmeter will be positive, but the magnitude will be different. So the total power will be like that. Positive power after reversing the or transposing the wattmeter coil connections. When the power factor is 0, that means the phase angle is 90 degree. So the 2 wattmeter reading, the magnitude will be 0, but they will be their direction or deflections will be opposite, so that the sum of the power will be 0. So we use for our experiment condition number 1, power factor condition 1 and the power factor condition 3. So these 2 conditions we must follow, so that by noting down the wattmeter reading, digital wattmeter reading, when the 2 wattmeter readings are equal, means a perfect unity power factor results. When the 1 wattmeter reading becomes 0, then the 0.5 power factor exists. So these are the conditions which can be set exactly with the help of the wattmeter reading and the phase shifting arrangement. So this is important procedure, how the power factor condition can be set or manipulated. So there are different runs for noting the readings or observation with 100%, 50%, 20% of the rated current at unity power factor, and observe the amount of the time using the digital stopwatch system taken for a certain number of Dix revolutions. And under this condition, and the 2 wattmeter reading should be in constant for unity power factor condition, as well as depending on the other power factor condition. So the formula to find the percentage error is this, where Kc is the experimental value of the meter constant, wattmeter reading, that is the standard wattmeter reading, and the time used by the stopwatch. And K is the meter constant which is specified by on the nameplate, that is by the manufacturer. So the percentage error according to the formula gives the error caused by the disc rotation, because meter constant is the least count of the meter due to the disc rotation. The under second type of run, that is short time test for 0.5 power factor lagging load. Phase shifter and the wattmeter reading, we can set what is the power factor, that is exactly 0.5. Under this 0.5 power factor, the reading over W2 will be 0. Run 2 is a long duration test. Here, the 30 minutes time are allowed. So before start of the experimentation, the energy meter reading should be noted down. That is the initial reading. So after completion of the 30 minutes, the energy meter reading, the dial reading should be noted down. And taking the difference, that is the final reading minus initial reading, what is the amount of the energy consumption in kilowatt hour, that should be calculated. At the same time, the actual energy consumed based on the standard wattmeter reading should be calculated using the formula. And the percentage error should be computed according to the difference of the two reading. One is D0, that is and DT, that is the final reading. So these are the formula. Run 3 is the creep test. That means the energy meter should be, the current coil of the energy meter and the wattmeter should be unenergized by switching of the circuit. How? This switch should be switched off position, so that there will be no flow of the current to the current coil of both the meter, that is wattmeter as well as the energy meter. Under this condition, the disc rotation is followed, is observed due to creep action. If the meter disc rotates continuously for more than one revolution over 24 hours, in fact, the creep is said to be present, otherwise not. What are the conditions? Essential condition must be followed up. First of all, the three-phase supply voltage should be balanced. Otherwise, there will be error in measurement. The reading should be recorded for all measurements connected to the setup. That is, the ammeter reading must be same, so that there must not be variations of the loading or the load current flowing through the current coil as well as the current coil through the test energy meter as well as the wattmeter. So these are the mandatory conditions must be followed carefully for carrying the experiment. And what we have obtained under the different run, so this is the typical sample reading. And the percentage error has been computed using the appropriate formula. You can notice that means if the load current has been reduced from 100% to 50% or even less than that 20%, then what will happen? If the load current is reduced, the total amount of the power, the sum of the two wattmeter, that will also decrease, and that has happened. As well as here, number of disc revolutions for 100% rated current is fixed around 40. So to complete the 40 disc revolutions over for a 100% load current, the time taken by using the stopwatch is 103 seconds. But when the load current has been reduced half, that is 50, so the number of disc revolution, instead of maintaining 40 complete revolution, it has been reduced to 20. Why? Because to avoid the waiting, so 20 revolution is sufficient to get the reading, and the time taken will be 103.83 seconds to complete the 20 revolution. If it was 40 revolution for the reduced loading condition, the time will be very, very high. So there is a savings in the time, waiting time. For 20% load current, the number of disk revolution, that means to set, is further reduced to 10. And the time taken to complete the 10 revolutions under 20% of the rated load current is 127.2. And the calculated meter constant according to the formula based on these rotations, disk rotations, are based on the time to complete the prescribed rotations are calculated using the formula. And these are the percentages. But if the power factor has been reduced further to 0.5, then the number of disk revolution to set should be further reduced to 20, 40, like that. Increased, not reduced, increased. So we get the sufficient amount of the time should be allowed, 61.54 and 60.10. That is, when the power factor 0.5 has been set, under short time test, the error in meter constant is 8.81, 8.51. In fact, there is a, that means there is a scientific reason that why under reduced power factor condition, the error will be small, because the number of disk rotation or the speed of the disk will fall also under reduced power factor. So the more will be the speed of the disk, the more will be the chance of the error in meter constant. So that is conceived, that is considered. Then for the long duration dial test over the 30 minutes, that is half an hour, what is the standard wattmeter reading, the sum of the reading, and the true energy consumed by these things in kilowatt hour has been calculated by summing these two readings over 30 minutes is this. So initial and the final reading that been taken from the test energy meter, and the difference of which is like that is 0.29. It is higher than the true energy consumption over the 30 meter in kilowatt hour, and the error become negative in our case. So that is the sample reading or interpretation of the sample reading. In run 3, that is for creep test, there is as such no creepage has been observed, because the disk has been energy meter when it has been released by the manufacturer, the creep should be avoided. So any creep should be eliminated by taking care, that means properly. So no creep was found for in our case. So these are the salient points for this expense. Unfortunately, you are unable to carry out in your own hands, because these laboratory classes is done in online conditions. So if you have any questions, then you can ask freely, because you have to make the report, laboratory report. What is the laboratory report? The objective of the experiment I have described or explained. B, draw the neat circuit diagram. The circuit diagram is available to you with instruction manual. C, make a tabular list of the apparatus. You have to list out all apparatus used for the experiments. D, enter the test data in the various runs. There are 2 runs basically, or 3 runs. Show the sample collection using the formula. Finish in tabular form of the calculated results for all the testing. So these are the reporting item you have to complete. Regarding the basic understandings or objective of the experiment, you can ask right now. After that, I will record your attendance. Then finally I will show the videography of the complete experiment. The videography is done by our technical staff in our laboratory. So if you have any questions, then please ask. If you don't have any proper questions, then I am recording that recording your attendance by calling the names or roll.
Okay, sir.
Shaming Hawk. Please respond.
Present, sir. Present, sir.
Vishal Barmon.
Yes, sir. Present.
Avneet Chatterjee.
Yes, sir.
Abu Said Sheikh.
Yes, sir. Present.
Ananda Chakraborty.
Present, sir.
Motibur Rahman.
Yes, sir.
Devraj Banerjee. Devraj Banerjee.
Present, sir.
Mousumi Soren.
Yes, sir.
Alamin Islam.
Present, sir.
Mohammad Mubasir Alam Midda.
Yes, sir.
Amisha Parvin.
Present, sir.
Jayat Datta.
Present, sir.
Susmit Rudro. Susmit Rudro. Susmit Rudro is absent. Robin Chalak.
Yes, sir.
Rishabh Mahajan.
Yes, sir.
Aritra Mal.
Yes, sir.
Biprodash Mandal.
Yes, sir.
Ruplekha Roy.
Yes, sir.
Indila Haldar.
Present, sir.
Rukshanda Hussain.
Present, sir.
Anubhav Rai.
Yes, sir.
Rudronil Sardar. Rudronil Sardar. Rudronil Sardar is absent. Polomi Das. Ovijit Das.
Yes, sir.
Manjur Alam Midda.
Yes, sir.
Nayan Soren.
Yes, sir.
Rajeshri Bhattacharya.
Yes, sir.
Jyotirindra Sarkar.
Yes, sir.
Shashwat Mukherjee. Shashwat Mukherjee.
Present, sir.
Swastik Kanjilal.
Present, sir.
Vinay Kumar Rajak.
Yes, sir.
Mohammad Yunus Ahmed.
Present, sir.
Jayant Mandal. Jayant
Yes, sir.
Mandal.
Yes, sir.
Shobik Nag.
Yes, sir.
Sambit Bishas.
Present, sir.
Akash Singora.
Yes, sir.
Devonik Borua.
Yes, sir.
So two are not present. One is Susmit Rudra
Sir, I am present, sir. Actually, my mic was not working at that time.
and another is Rudronil Sardar. Rudronil Sardar is not present. So now I am going to show the videography of the whole experiment.
Students, today we are going to demonstrate the experiment calibration of three-phase water volume.
Can you see the videography? All of you?
Yes, sir. But the sound is
Okay.
not clear.
Okay.
Secondary of this transformer rating 4 volt. That 4 volt is coming to this US. Actually, induction type. Now you can see this is the circuit diagram, and previously whatever I said that this is the step. You can see the full starting from this the secondary part of this transformer. Okay, from there it is going to A. There is an ammeter. R1. So this is the transformer. From there, we connected it to the R1. Using series, so I can connect it R1 first, then it can go to the ammeter. So we have connected it to the R1. From there, it has gone to the ammeter. Actually, this is a combined meter. This one is the watt meter and volt meter and ammeter also. Okay, it's a combined meter. So we connected it to this meter. So from here we can check the current. Now this meter is set in voltage. It is showing the voltage. Now if I change the mode, you can see the current. So this is the current now. So we connected it to the ammeter. You can consider. So from the ammeter, it has gone to the watt meter. So this is the watt meter. Watt meter is current coil. So it is already connected to the watt meter. Okay. And from the line has gone to the second watt meter. So you can see this is the second watt meter. Here also it is connected. So physically when you see this is the transformer, this transformer is this one. From here it is going to the R1. This one is R1. You can find it in your circuit. This is the R1. And this one is the W1. So that this one is W1. Okay. And this is the what? Three-phase watt-hour meter. Actually in circuit, this is the three-phase watt-hour meter. You can see this is the three-phase watt-hour meter. This one is W1. This one is W2. R2, R1. Okay. And you can see this is the rotating of this watt-hour meter.
Now you can see that means the brake magnet and the induction disc on an open system, the front chassis has been opened up. So this is a registering mechanism decade dial. So this part is for induction disc type, which moves in the brake magnet. Without the brake magnet, there is no steady speed. And the disc is coupled to the two elements, that there are two discs which are coupled to the mechanical linkage. And this registering mechanism on the top uses a set of pinion arrangement. So please note or see the construction and details of the energy meter practically.
And this one is the important device. This is the phase shifter. Actually, we are not using here load means actually variable load. That means we are not using here any variable inductor or any variable capacitor by which we can change this angle of the circuit. We are only using R1 and I2. By changing this R1 and I2, actually change the current. R1 these two resistances are resistive load. So we are not here using any inductive load or variable capacitive load. By changing which load, we can change the phase angle. So here we are using phase shifter. Okay, phase shifter for phantom loading or fictitious load. Okay, so by changing this phase shifter, we will change the phase angle of the circuit.
In fact, the angular positions of the rotor relative to the stator, that is the three rotor windings in three-phase system, these are rotated by this gear. So you can note down the scale of this pointer, how much is the rotation that is occur in terms of the phase angle. So that is, but we are not using we do not follow this scale, rather we will follow the wattmeter power factor conditions. So this is the thing.
Now we are going to the experimental part. So we have total three runs. Run one, time test unity power factor. Okay. In this test, actually we will take the power factor 1, that means unity power factor. In unit power factor, we change the 100%. First reading will be on 100%, then it will be on 50%, then it will be on 20%. Accordingly, we will check total revolution time. Okay. In unity power factor at 100% load, the first reading will be at 100% load. Will take the time for 40 revolutions of the disk. 100% load will take 20 revolution time. It will take the time for 20 revolutions of the disk, and again in 20% of load will take the time for 10 revolution of the disk. Okay. Now run 1B, the second part of the third one. First of all, of this run 1B, we will change the power factor, value of power factor. How? Already I told you, we'll make the value of power factor 0.5. Okay, by changing the phase shifter. Then in 0.5 power factor for 100% load, we'll take the time again. We'll take the time for 20 revolution of the disk, and in 50% of the load, we'll take the time for 10 revolution of the disk. So our run 1B is the short time test on 0.5 power factor for 0.5 power factor load. Okay. Then next test is run 2. Run 2 will be the dial test at full load unit power factor. Okay. And the third and the last test will be the run 3, that is the clip test. Okay. Now we will go to our experiment. We will see how we will perform this experiment. As I say, this meter is a combined meter. That means this one is W1 and as well V1 and I1 also. And this one is W2, V2 and I2. So from these two meters, we can see the value of V1 and V2. You can see the value of V1 is now 109 and V2 is 110. Now our first step, that will be to set the current to the 5 ampere. We'll change the value of R1 and R2 to make the current 5 ampere. Now we'll change the mode and set it ampere. Now this ampere, you can see that current is changing. You can see now the 5 ampere current already set into ammeter. Okay. The total current is going to this energy meter and the wattmeter is 5 ampere. Now you can see that this is rotating. So now next step will be to make this power factor 1, that is unit power factor. As I told earlier that the phase shifter will use phase shifter make the power factor 1 by varying the phase shifter. Now at first now we are changing it to power for both the watt. Now you can see this is in power watt. So how can I understand that it is in unit power factor? Well, same power will be shown in 2 wattmeters. The value of the wattmeters will be same. Okay. So when now you can see that we are varying this wattmeter in phase shifter. We are varying this phase shifter. We'll take it to the same value. Now you can see where changing it. This one is decreasing. I will to make it safe. Make the value. Now you can see both the values are same. In this condition, you can say the power factor of the circuit is 1. It is in unity power factor. Okay. Now our setup is ready to be ready. Okay. So you can see these discs are rotating in the energy meter. So whatever I said, we will take in full load. It is in full load condition. 5 ampere will be the full load condition. That is 100% load for this experiment. So it is in now full load condition and unity power factor. So as I told earlier, that for 100% load and unity power factor will take 40 revolutions of this disc. You can check only one disc. So how you check that? You can see that a mark is there. Okay. So
there is a black mark. So by counting how much time the black mark passes during rotations, so this will take this will cause one complete revolutions like that.
when the mark come back again here, that will be one revolution. That way you have to count 40. And when you count that time, you have to start this stopwatch. So you have to start this stopwatch and wait for 40 revolutions. And then when 40 revolutions will be over, that time you have to stop this stopwatch and you have to take the reading. Okay, now we're starting. That's it. This, start. Already stopwatch is working. And I'm counting the distribution. Okay. So in 40 revolution, I got the time that is 102.4 seconds. Okay, in 40 revolution. So you have to note it down here. Time taken in seconds, and also let's note the wattmeter reading, that is W1 and W2. I'm just showing two values. So W1, W2, the number of disc revolution 40 we know already, and time taken, that is the 1.4, and calculated meter constant. All the formula has been given to your worksheet. From there, you will get the calculated meter constant. This one is the Kc. You have to calculate the value of Kc using this W1, W2, and T. When you are going to find the percentage of error, at that time one value you need to know, that is the K. Kc we are calculating from here Kc, but K, the value of K also you have to know. And the K, the rated, that is the rated meter constant of this meter. It is written on this cover of the meter. You can see that is 2004.
See the rate meter constant specified by the manufacturer, 2400 revolutions per 1 unit of electricity, 1 kilowatt hour.
So this is the value of E. And you also have to find out the percentage of error. Okay. Now, for 50% also same procedure that has to be done, the same procedure, but for 20 revolution and 20% load also, you have to take reading for 10 revolution. More or less same procedure for run 1B also. But before starting the run 1B procedure, you can see that the power factor is 0.5. So we have to make the power factor 0.5 by varying the phase shifter. Now we will vary the phase shifter. So here also how we know the when the power factor will reach to the 0.5. Okay. So now you can see when the total load will show in single wattmeter. In 1 wattmeter, it shows 0, and the single wattmeter, the total load will, total load, not the total load, I'm sorry, it will show the total power, it will show the single wattmeter. Now you can see the value of W1 is decreasing. I am actually varying the reference shifter. Now you can see the value of W1 is decreasing and the value of this is increasing. Now, yes. Okay. Now total full power now showing in the W. So this condition, power factor is 0.5. So now we'll start run 2. In run 2, you can see it is already written that just at full load. This is full load. Okay. Now we are filling it full load. That is 5 ampere. Already I have mentioned, and it will be again in unity power factor. So we again set it to 0 degree. That means unity power factor. You can see the wattmeter to the wattmeter make the same reading. Same. Okay. Now you can see showing the same reading. So it is proper reading. And now in run 2, it's a long run. Okay. So we'll check the dial reading of this energy for 30 minutes. So we will run it for 30 minutes. So before we start the time counting, we will take the reading of this dial. Okay, this dial reading, we note the reading, and after 30 minutes, we note the reading again. So by taking this dial reading, we will find the total energy consumption in 30 minutes. Okay. Now, our last test is creep test. For creep test, we will energize the current coil. So we will switch off the power that supply. We will switch off the supply of current coil. So only potential coil will be excited. There will be no supply to the current coil. Which means you can see we already energized the current coil. So in that condition, the potential coils are energized only. In that condition, if the disc will rotate, we can say in the meter there is creep. But if disc will not rotate, so there is no creep in this meter. Disc is not rotating, both the discs are not rotating. So you can say that there is no creep at all. Thank you everyone. So I think you all understood the experiment procedure. We try to explain it properly. If you have any doubt, please ask. Then we will try explain you completely. Thank you.
So you have watched the videography and the details of the performance of the experimenting this experiment. So that very important point for your understanding, that means the effect of the load power factor on three-phase power measurements or the three-phase energy measurements, number one. And the second important question that will definitely arise, that means how, when we reduce the loading condition from 100% to 50%, why the prescribed revolution has been reduced. The only reason is that means if we can save the same amount of the deep revolution, that is like 40 for 100%, 50%, 40, then how the amount of the time to complete the revolutions by the disks will be much larger. So to avoid the excessive delay to complete the revolution, that can be avoided by assigning the number of disk rotations under reduced loading condition as well as the reduced power factor condition to lower value. That is, from 40 it has been decreased to 20, then 10, etc. So these are important questions. Why? Because because according to the formula of the energy, when the power factor as well as the rated load condition has been reduced, the speed of the disks will fall. The speed of the disks will be lower. Theory and the mathematical derivation, the speed of the disks will require. Speed of the disks will depend on the amount of the watt, amount of the constant power flow. So this is a very important question. You must be able to answer. If you have any questions, still further in your mind, you can ask the questions. It will be supplied via the videography. Already I have supplied the videography to a group mail. And this presentation as well as the, that means what are the reporting item, what are the things you have to report, prepare the report, that will be supplied immediately to your group mail. So thank you for attending the online laboratory classes. Okay. So if you have any questions, no questions. So thank you all for attending the online laboratory classes.